Hello, welcome to this video where we take the multivariable approach to implicit differentiation. And now we extend it to 3 variables. So the issue is that we have a function of x and y, but there's no way to write the z as a formula in x and y. The x, y's, and z's are all entangled together. And so there's no way to solve z as a function of x and y. And so what we do instead is set everything equal to 0, move all the terms over to one side, and call that function capital F. It's a differentiable function, and since the equation is now set equal to 0, then what's going to happen with the z part is that it is multivariable. We don't know how to write it as a function of x and y, but we treat it as if it's a function of x and y, multivariable. And so we create this just call p equal to this f function. The derivative of p has to be 0, both with respect to x and with respect to y. Let's look at it with respect to x on this slide and then y on the next slide. So let's use the chain rule to help us figure out then why the formula is what it is. So I'm looking for the derivative of p with respect to x, partial derivative that is. And what I have to do is take the derivative of f with respect to x multiplied by del x, derivative of f with respect to y multiplied by del y, del x, derivative of f with respect to z multiplied by del z, del x. And then the other side of the equation equals to 0, so that derivative will be 0. Let me substitute, go back in, changing the subscript notation because it's so much easier to deal with subscript notation. So f's partial with respect to x is f sub x. It's times by 1, del x, del x. F sub y is f's partial with respect to y, but it's times by dy dx. And that's going to be 0. And then f's partial with respect to z is times dz dx, and that's what we have to solve for. You see, why is the y partial with respect to x equal to 0? Because you're supposed to hold y as a constant. And so its derivative with respect to x is 0. And so therefore we have the following formula then. The other variable zeroes out. The other, like f with respect to y part zeroes out. Now we're going to solve for z with respect to x by subtracting the fx over and dividing by fz. So here's the formula. If you have a multivariable function that is defined as an implicit function, no way to just have z equals f of x, y, but we can treat z as equal to g of x, y, though, with just symbolically. And now we can take z's derivative with respect to x. And we can just do this all over again to get z's derivative with respect to y. Okay, so I went quickly through that part, but here we go, where we'll switch to subscript notation. We have f's partial with respect to x. Del x, del y is 0. F's partial with respect to y, del y is 1. F's partial with respect to z, and then del z, del y is what we're looking for. Del x, del y is equal to 0 since x is a constant when you differentiate with respect to y. So then our job is to solve for del z, del y by subtracting the fy part over because that fx part zeroes out and dividing by fz. So that's why the formulas are what they are. Now let's use them in a problem. I have this function that is just, the x, y, and z are just entangled. They're in an entanglement. There's no way to untangle and have z equal to a function of x and y. So the x, y, and z are entangled in an entanglement. Okay, so what do? It's implicitly defined, okay? It's not explicitly. If you could untangle the entanglement, then you could have it as z is a function of x and y, but you can't. So you have to treat it symbolically like that. So here's how we deal with the entanglement. We ship everything over to one side. We could actually leave the 8 and the log 2 on the right-hand side. I said to set everything equal to 0, but we could actually set it equal to a constant. And 8 plus log 2 is a constant. But let's go ahead and move them over to the other side. And then let's use the formula. We're interested in finding z's partial with respect to y, even though there's no way to write z as a function of x and y. At a particular point when x is 3 and y is log 2 and z is 0. All right, so we take the y partial, we take the z partial, we plug in, we divide. That's all there is to it. First term is y derivative. E to the xy times x. Second term is y derivative, 0. Third term's y derivative is a 1, and the rest of that junk is constant. How about the z partial? There's only one term with the z, so theoretically you probably could untangle it and solve for z, but then you have to deal with arc sign, so let's not do that. Every function that is explicit can be treated as implicit, not the other way around though. So although this might be maybe you might be able to do it algebraically, still let's treat it like it's implicit and solve it this way. All right, so the z partial comes only from the second term there, and it's cosine of xz times x. Now we divide and we plug in. We could have plugged in, earlier before going to the division, but yeah, x is equal to 3. Y is equal to log 2. So 3e to the 3 log 2 plus 1 is the numerator. Denominator is 3 cosine of 0. 3 times 0, 0. Cosine of 0 is a 1. So the denominator is a 3. What's going on with this e to the 3 log 2? You can't cancel the e and the log. First you have to get rid of the 3 using the log property. A times the log of b is the log of b to the a. And then you could cancel. It's really 3 times 8. 2 to the 3. So that's 24. Plus the 1 is 25. The answer is 25 over 3. There was that negative out front. And you did it. All right. Thank you for watching. My name is Nakia Rimmer, helping you through this multivariable calculus journey. And now we're going to end this set of videos on the partial derivatives and the chain rules, and be able then to move forward into applications of the derivative. All right, please reach out to me if you have any questions. Comment down below, like and subscribe, share. Check out my webpage, CalcCoach.com. And thank you for watching. I'll see you in the next video.